Okay, chemists, in our last lesson in this unit, we're going to focus on some nomenclature techniques that we need specifically for alkenes. We've been making alkenes in elimination reactions, and actually our next unit is all about the reactions of alkenes. So let's pause on new reactions and just talk about nomenclature. We know how to do nomenclature already, even for simple alkenes. For example, if I look at this 5-carbon chain right here, I would number it 1, 2, 3, 4, 5. So this is a pent derivative. It's not pentane, it's pentene. I gotta say where the ene starts, that's on carbon 2. So this would be a 2-pentene. And specifically, those 2 hydrogens coming off of the alkene carbons are pointing the same direction. So this is cis-2-pentene, and that's perfectly acceptable. You can also have cis-pent-2-ene and put the number in front of the suffix ene, different from trans pent-2-ene or 2-pentene. But what if I have an alkene where cis and trans don't really seem to cover enough of the molecule to name it that way? It's not sufficient. So here is an alkene where I say, is this cis or is this trans? Based on the rules we have, I don't know, because there's only 1 hydrogen coming off of one of the alkene carbons. So we have to use a new nomenclature system called the E/Z naming system. Don't worry, it's easy to name alkenes such as this. So here's how it works. You find your alkene, there it is. And then you look at the 2 sides, the 2 carbons of the alkene. I'll put a dotted line between them. And on each carbon of the alkene, there's 2 other groups attached. We have a bromine and a hydrogen on this carbene on the carbon on the right. And we have a methyl and a hydroxymethyl on the carbon on the left, and we prioritize them. We prioritize them the same way we prioritize things according to the Kahn-Ingold-Prelog rules for R and S nomenclature. So you go out 1 atom at a time, you hit a higher atomic number, that gets you a higher priority. So on the carbon on the right, if I had to prioritize bromine versus H loses and bromine wins in priority. On the left, we have methyl versus hydroxymethyl. Well, it's carbon versus carbon, so we tie. We go farther than that. We get to oxygen versus HHH, so the hydroxymethyl wins. So these 2 high priority groups are on the same side of the alkene. The high priority groups are cis to each other. They are together. So we use the German word for together, meaning zusammen, and we abbreviate this as a Z alkene, because they're on the same side. Ha. So now we can actually name the whole thing and put the Z in front. Let's figure out how we name this. Well, find the longest carbon chain. I think it's only 3. Find the highest priority functional group. It's actually the alcohol. So carbon 1, carbon 2, and carbon 3. And then it looks like we have an all on carbon 1, we have a methyl on 2, a bromine on 3, and an ene on 2. I put all that together, and we get 3 bromo, alphabetically first with the bromo, 2 methyl, prop, because it's a 3-carbon chain, dash 2 dash ene, because that's where the alkene is, dash 1 dash all. However, I need to specify the alkene geometry, so you put a Z in a pair of parentheses all the way out in front. That is how you name that tiny little molecule. Whole point being that cis and trans is no longer sufficient. We switch to Z for the same side, and then E would be opposite. German for entgegen, meaning not together, meaning opposite. So let's practice this right now and take a look at a couple of alkenes, also called olefins, and classify them as opposite or together, E or Z. So for the first one, I'll just draw a line through the alkene. Who's higher in priority on the right? It's the chlorine. On the left, who's higher in priority between the methyl and the H? It's the methyl. These are on opposite sides, so this is an E alkene. Right next to it, if I cut the alkene right down the middle, chlorine beats H. Who wins, methyl or methyl? It's a tie, so this is neither. You can't classify that as E or Z, so only use it when it's relevant. The third one, cut the alkene in half. On the right-hand side, ethyl beats methyl. On the left-hand side, phenyl beats methyl. This is a Z alkene. And lastly, there's my alkene. On the left-hand side, methyl beats H. On the right-hand side, my aldehyde beats my hydroxymethyl. This is a Z alkene. So E, neither, Z, and E. And now let's put that together and do some practice nomenclature. Here's a chiral alkene containing molecule. If I number my carbons, I want to get to the alkene as fast as possible. 1, 2, 3, 4, and 5. So this is a pentene. I can tell right away it's trans, so I could say trans or I could say E. Those are both acceptable, by the way. If you have a hydrogen on each carbon, you can use either one. And then I have a bromine on carbon 4. It's also an asymmetric carbon, so I need to, in addition, figure out if that's R or S. So the H is coming straight out of the page. My highest priority would be the bromine, followed by this vinyl group, followed by the methyl. So 1, 2, 3 in a clockwise direction with H coming out. I get an S asymmetric carbon. So this is S, and the alkene is going to be E. So I put all that together. This is a pentene. It's a 4-bromopentene, and the ene is on carbon 2. So I get 4-bromo-2-pentene. But then I have to specify the alkene geometry and the asymmetric carbon out in front. You do the asymmetric carbon first, so it's S, comma, E, dash rest of the name. Just like if you have multiple asymmetric carbons and you have to designate which one is R or S, same thing if you have multiple alkenes. Which alkene is the E and which one is the Z? Very similar way of thinking. For B, this is an alcohol-containing functional group, so 1, 2, 3, 4, 5, numbered left to right. Looks like we have an OH, so an ol on 2, a bromo on 4. I have an asymmetric carbon that if I check, that is S. And then if I look at the alkene geometry, higher priority bromine on the right, and then stuff on the left. So this is a Z alkene. So my name becomes S, comma, Z, dash, it's a 4-bromo, pent, actually there's no hyphen if there's no number. Let's back up. Pent, 3-ene, 2-ol. Notice you can put the number right in front of the suffix when you have sort of multiple suffixes, as opposed to putting the 3 in front of the pent. You could do that as well, it would be implied. And then lastly, one more, this is just a hydrocarbon. Remember, the isopropyl means you've got a couple of other carbons here, so it's okay to change the drawing and make it easier to see if you want, and then you can actually name it a little bit more easily. There we go, so 1, 2, 3, 4, and 5. And looks like we have a 2-ene. This is a pent 2-ene, and it has a couple of methyls on 3 and 4. And also I need to say what the alkene geometry is. On the right, methyl beats. On the left, isopropyl beats. This is E. So E goes in the front, followed by 3, 4 dimethyl. Got to say where both methyls are. And then pent 2. E. Okay, now let's turn this around. Let's take some names and turn them into drawings and see if we can figure out what they look like. 3-methylene cyclohexene. Remember, start with the end of the name first. Cyclohexene. So I have a cyclohex and an ene in the ring. They didn't number it, so I know that means since I'm in a ring, it's sort of arbitrary where the numbering is. So I know that one of those is carbon number 1, if I imagine those numbers like so. And then relative to that, I have a methyl on position 3. I'm going to make those numbers disappear and put a methyl. Actually, careful, it's not a methyl, it's a methylene. What's a methylene? That's a CH2 group. CH2 group is a methylene, as opposed to a methyl. So that means I have to have that extra pi bond right there. That's 3-methylene cyclohexene. To the right of it, E-pent 2-ene. This is a pent, so 5 carbon chain. I have an ene on carbon 2. Now I arbitrarily just drew it right there with trans alkene geometry. Let's make sure that does fit E. Yep, that's the opposite. So done. C. Multiple alkenes, so multiple designations of where the E and the Z geometry goes. This is an octadiene, 2 alkenes, so octa, 8 carbons, 2, 4, 6, and 8. We have a bromine on carbon number 3. There it is. And then I have to have an alkene on carbons 3 and 5. So then carbon 3, meaning 3 to 4, and then 5, meaning 5 to 6. And now I gotta check, is my alkene starting at carbon 3, is it Z? Well, I would have a higher priority bromine and a higher priority rest of the chain. Yep, those are on the same side. That's Z, so I got lucky. I just drew it correctly first. And then that one, is that E? Well, I have a higher priority here and a higher priority ethyl there. Those are on opposite sides. So yep, that's E and that's Z, so this is correct. If not, I have to redraw it to show that kink in the alkene in a different direction. Lastly, this is a challenging one, so I would hit pause and just try it and see how far you get, but here's what we get. If you look at the end, it's a cyclohexane, so I have a 6-membered ring. I have a methyl on position 2. It is a 1-chloro, 3 complicated branch, and then a 2-methyl. So I'm going to number my carbon chain 1, 2, 3, 4, 5, and 6, and figure out where stuff is. 2-methyl, that's easy. Just put a methyl coming off of it. And then 1-chloro, that's also pretty easy right there. And then off of position 3, I have this complicated branch. A complicated branch goes inside a pair of parentheses. So this is a hexenal branch, and on carbon 2 of the branch is where I apparently have my ene. So that means I have a 6-carbon branch, 1, 2, 3, 4, 5, and 6, and it has an alkene on the 2nd carbon in, which would be that one, because you have this subset of numbers on the branch, 1, 2, 3, 4, 5, 6, where in position 1 of the complex branch is the one that's directly attached to the ring. That's supposed to be an E alkene. Yep, it is. I luckily just drafted it correctly. And we're not done. I have 3 asymmetric carbons here, and they're at the 3 positions I just drew. So I need to make sure they are respectively S, S, and R in my picture. So to make the chlorine S, I actually have to change that to a dashed line. To make the methyl S, I have to change that to a bold line. And to make the hexenal branch R, I have to make that also a bold line. I'll let you go back and check and make sure that those fit from the R and S nomenclature. At the bottom of this, since this is our last lesson of the unit, I just have some summaries and some features of alkenes that you should know. Alkenes have that extra bond. They have a pi bond, so they are stronger than an alkane bond. Typically, you cannot rotate around a pi bond, so you're locked in this E or Z geometry, as opposed to where you do get free rotation around a single bond. There's a rule that says more substitute alkenes are more stable. We know this already. It's Zaitsev's rule, so we have a more stable alkene for most E2 and E1 reactions, as opposed to the less stable alkene. And then there is another rule called Brett's rule, which says that bridgehead alkenes are very unstable. And what's an example of a bridgehead alkene? Well, remember when we have these bicyclic compounds like so, the bridgehead carbons are the ones that are shared by the multiple rings, and you cannot have a bridgehead alkene like this. It is very hard to do in the confines of even fused 6 and 5-membered rings like that one. The reason is because this cannot be planar. So sometimes we actually end up violating, or look like we're violating, Zaitsev's rule, and if you had to do an elimination where you got an alkene product, maybe you would get this one. This is called norbornene, even though this is technically the non-Zaitsev alkene, if you imagined making this from some halide that you started with. Okay, that wraps up this unit on substitution and elimination reactions. There's plenty of practice left to do. Good luck, and thanks for watching.